Okay, so here's the photoelectric effect part 2. This is the last lesson, third and last lesson of this week. And we're going to move on with having a look at some calculations. Some of this work will overlap with the last lesson. Right, so first of all, energy carried by photons. So photons carry energy, and how much energy do they carry? So we know that energy is carried by photons. Just how much we can work out in terms of numbers. So let's have a look. Here we go. Energy is proportional to frequency. Here's our whole electromagnetic spectrum with radio, Roy-Gebiv, UV, X-rays and gamma up this end. And we know that this has a low frequency. Radio has a low frequency. Gamma has a high frequency. So if radio has a low frequency, then the amount of energy carried by radio photons is also low. The gamma rays have a high frequency, so the energy carried is also high. In other words, energy is proportional to frequency. The bigger the frequency, the larger amount of energy. That's a proportional sign. That's that fish-shaped thing. Now, we can't do calculations with proportionality. We need to replace the proportionality with a constant multiplied by the frequency. So K is what is called in physics a constant of proportionality. Okay, so to get the amount of energy actually equal to the frequency, we have to multiply the frequency by this constant. And this constant K is called Planck's constant. And it's given the letter H. So we can rewrite our formula. Instead of any constant, we're going to say it's specifically Planck's constant multiplied by the frequency f. Now, Planck's constant is a number that is on the data sheet. E equals hf is a formula that's on the relationship sheet. And h is 6.63 times 10 to the negative 34 joule seconds. And that's on the data sheet. You don't need to remember the number. I suppose you don't really need to remember the formula. You can look it up, but you ought to know it, and we know how to use the formula. And that's where we'll be going. We're going to look at some calculations here. Right, so down the bottom end, the radio end, energy is low because frequency is low. Let's have a look at some numbers. Now, we're mainly interested in light round about ultraviolet, because we've said that anything below ultraviolet, red, orange, yellow, or white light even, any of the colors that make up white light, if they shine onto a piece of zinc, if the photons incident on the zinc, as it's known as, photons incident on the zinc are white light, then the electrons in the zinc are not going to get released. So we're mainly interested in ultraviolet. A lot of our examples will be based around what happens with ultraviolet light. So let's have a look at some examples, or an example with ultraviolet light, and we'll get some information about the frequency of ultraviolet light from the data sheet. Actually, that's not true. What we'll do is we'll get some information about the wavelength of ultraviolet light from the data sheet. And again, you don't need to remember numbers. You can look them up. So UV light on the data sheet, and you'll find some wavelengths. Now there's two wavelengths that are given on the data sheet, and they're connected with ultraviolet light that is produced by glowing hydrogen gas. So you take some glowing hydrogen, you take some hydrogen gas, plain and simple hydrogen gas, you put it inside a sealed glass container, and you pass electricity through it. That's just how sort of old-fashioned light bulbs work. So imagine you've got a light bulb, and it's full of hydrogen gas, and we'll pass electricity through it somehow. In fact, a lot of these bulbs have two ends on them, so you can pass the electricity in one end and out the other, without the need of having, like in a light bulb, without having a piece of wire. So we're actually going to pass an electric current through the hydrogen, and the hydrogen glows. And the gas glows and it gives out light of different frequencies, and that's because the light is made up of different wavelengths. So if we go and have a look on the data sheet, there are two wavelengths that are given, and I'm just going to pick one of them, 389 nanometers. And I suggest you go off and you have a look and you familiarize yourself with the data sheet, and you can see where this information comes from. And I'll write that again. Okay, now that's a wavelength, and that is not much use to us because our formula that was invented by Einstein, that has Planck's constant in it, actually has a frequency. So what we would need to do is we would need to convert that into a frequency. So given this wavelength, we're going to convert to a frequency. And this is a bit of National 5 stuff, and you'll know the formula V equals F lambda. This is on the relationship sheet as well. So what we can do is we can rewrite that, and we can say F is V over lambda. Now what's this V? It's actually the speed of light, and so we can put in 3 times 10 to the power of 8 in there, and then we can divide by 389. Now nanometers, nano, and you're going to have to remember this because nano and all these other prefixes, micro, milli, all the powers of 10 are not shown on the data sheet. So you need to know that nano is times 10 to the power of -9. And then we can work out the frequency, and you do that and you get 7.7121, just running out a little bit of space here, times 10 to the power of 14 hertz. So I know that's a little bit dark down there. I'll just move the board across a little bit so you can see that. You should be getting all this written down on your lined paper to go into your folder. Okay, so we've found a wavelength from the data sheet. We've converted that to a frequency, and now we can move on and we can use that in the E equals HF formula. So we've got E equals HF. So we've got this 389 nanometer wavelength photon, which has a frequency of 7.7121 times 10 to the power of 14 hertz. Now I've actually got 1, 2, 3, 4, 5 significant figures here. I don't want to cut this down to 3 because I'm going to use this in the next stage, which is E equals HF. And if you cut this down too soon to 3 significant figures, then you're building in inaccuracies in your final answer. We haven't got the final answer yet. This is just an intermediate stage. So we're going to work out how much energy is carried by this photon of UV light. So it's Planck's constant. I'll just move this down a little bit so I can get this fitted in here. 6.63 times 10 to the negative 34 multiplied by the frequency we've got, which is 7.7121 times 10 to the power of 14. And we do that sum and we get 5.11 times 10 to the negative 19 joules. And this I can give in with 3 significant figures or 2 decimal places. So that's the energy carried by that one single photon. And now that energy may or may not be good enough to remove an electron from our bit of zinc plate. So here's our bit of zinc plate. Remember, there's all these electrons here. This photon is going to come whizzing in, and we have to be able to work out whether that energy is enough to remove this electron, which is locked into the zinc plate. And we'll come back to that in a little bit of time later on. Okay, now let's just go back to the formulae. V equals F lambda. So F equals V divided by lambda. And E equals HF. So if I substitute this formula here into this formula here, I've got E equals H, and instead of F, I'm going to write V over lambda. So I've got a single formula now which combines these two. And you'll be familiar with combining and substituting a formulae from before. Now, this isn't any old velocity. In National 5, this could have been a velocity of a water wave, for instance. This is always the velocity of light. And as we know, the velocity of light can be given the symbol c. So this can be rewritten as E equals hc divided by lambda. This is not on the data sheet, but it's a formula that you could use to work out the energy carried by a photon in a single formula, rather than do what I just did, which was work out F and then substitute it into E equals HF. So if we did that all in one go, for that 389 nanometer photon, then I could do it all in one go, and then I could get how much energy does it have. It has E equals H 6.63 times 10 to the negative 34 times 3 times 10 to the power of 8, all divided by 389 times 10 to the negative 9. And that will enable you to get the answer in one go. And you'd still get that answer of 5.11 times 10 to the negative 19 joules if you do all that in one go on your calculator. Okay, let's have a look at the formula in just a little bit more detail. That combined formula. Now, some of these things are constants. H is Planck's constant. C is a constant. It's the speed of light. So what we've got here is two numbers that are always fixed. And we have lambda, which may vary. It could have been the other wavelength of ultraviolet light that you got from the data sheet, or any other color of light that you wanted, and we could work out the energy. Now, because lambda is on the bottom of the formula, that has implications as when lambda gets bigger. So on the bottom of the formula, if this gets bigger and these two are fixed, then as lambda increases, then energy, E, decreases. So a bigger wavelength as you go more to the left down to the end of the electromagnetic spectrum. If you start with radio here and finish with gamma up there, as you go increasing wavelength, the amount of energy decreases. If you want to have a look at E equals HF, this is a constant, H is a constant. If the frequency here in this formula, if the frequency increases, then E increases. And you should be aware of how you can take a formula like this and you can actually discuss the effect of the wavelength. When lambda increases, E decreases. The opposite would be true when lambda decreases. When the wavelength decreases, the energy increases, and so on with this formula here. So you need to know how the effect of changing variables inside these two formulae actually affects the amount of energy. So with the frequency of the photon and the wavelength of the photon affect the amount of energy carried in opposite ways. Okay, that's that little bit. So we've got then a way of finding out the energy of the incoming photon because E equals HF. And we've got then our bit of zinc with our electrons embedded in it, and what effect is that incoming photon going to have. Right, now this piece of material, the material itself has its own characteristics, and one of the characteristics excuse me one of the characteristics of the zinc is something called the work function. And the work function is the minimum amount of energy required to release an electron. Okay, the minimum amount of energy required to release an electron. That work function, symbol W, is equal to HF0. We also know that F0 is something called the threshold frequency. Talked about this before. So if the incoming photon has a frequency that is less than the threshold frequency, then the electron stays where it is. If the incoming energy carried by the photon is exactly the same, if this frequency is exactly the same as the threshold frequency, then the amount of energy that the photon carries is just enough to release the electron, and the electron is released. Incoming photon hits an electron, one photon, one electron. That electron is released and it just sort of hovers around minding its own business without doing anything. If the energy carried by the incoming photon is greater than the threshold, is greater than the work function, if the frequency is greater than the threshold frequency, then that electron can actually use the extra energy and the electron can zip off at high speed with some amount of kinetic energy. So the work function is something that's linked to the material and is not to be confused with the energy of the incoming photon. So we've got three conditions. I'll just go over those again. If this energy is too small because the frequency is too low, if that energy carried is less than the work function, the electron will stay inside the zinc and won't get out. If the energy carried by the photon is the same as the work function. That means the frequency, the incoming frequency, is the same as the threshold frequency. Then the electron will just sit there. And if the energy carried by the photon is more than the work function, that's because the frequency is higher than the threshold frequency. Then the electron can be ejected and it can move off with some sort of speed. That's three things we need to look at. Three things we need to look at. And the sort of questions you can get given will say, well, what happens if this photon has this amount of energy or it has this amount of frequency? Can you work out the energy? Can you work out the work function? Compare the two. Energy is less than the work function, nothing. Energy is the same as the work function, electron just released. Energy more than the work function, the electron can zip off at speed. So, example. So if the threshold frequency for zinc is 1.02 times 10 to the power of 15 hertz, what is the work function for zinc? So this is all about the zinc at the moment. So the formula for the work function is equal to hf naught. F naught is the threshold frequency. H is Planck's constant. So we can work out what is the work function. And that is 6.63 times 10 to the negative 34 multiplied by that number there, 1.02 times 10 to the power of 15 hertz. I won't put the hertz in the formula. And that is 6.76 times 10 to the negative 19 joules. You'll get plenty of time to do some of these yourself later on, but you just need to get these down as worked examples. Okay. So that's the energy needed to get rid of one electron. Anything less than that 6.76, the electron's going nowhere. If the photon carries exactly that amount of energy, then the electron will just be released. And if that is more, if the frequency and the energy of the incoming photon is more than 6.76, then the electron can escape with some speed. So we'll write down those three because I've been talking about them long enough. Let's write them down. If a photon of incoming light has less than the work function, then so less than the work function energy, then the electron stays in the metal. Next one is about what happens if it's equal. And I'm sure you ought to be able to write these yourself. So that's scenario 2. First one is if the energy is less than that, then the electron doesn't budge. If the photon coming in has exactly the same amount of energy as the work function, the electron is just emitted and just sits there. It just hangs around just outside the metal, just on the edge, doesn't do anything. And I'm now going to have to rub out that to fit in my third scenario, number 3. And that is if the photon so if the photon of incoming light has more than the work function energy, then the electron will not only be emitted, the electron can actually leave the area around the zinc plate and it can escape with some speed. And I'm going to qualify that and say then the extra energy carried is converted. That's the extra energy of the photon is converted to kinetic energy to enable the electron to escape at speed. And we know that EK is a half mv squared, and so we could work out the speed of the electron. And we've done calculations like that earlier on. Let's just have a look. If you're finding all this a little bit difficult, let's have a look at some numbers. And I'm not going to use numbers that are times 10 to the negative 16 joules. We'll look at big numbers just to demonstrate this. I'm sure that many of you will be picking this up straight away. So circumstance number 1, let's have our zinc plate with our electrons in it. And I've got a photon coming in. And I'm just going to pick some big numbers, okay? Let's say that the work function is 12 units. And when I say big, 12 is nothing like something or other times 10 to the negative 19. Not going to bother with the scientific notation. So the work function is 10 units, and the incoming energy is 10 units. Okay, now 10 units is not enough to overcome the energy needed to get the electron out, because you need 12 units of energy to get the electron out, and 10 units just won't have any effect. So the electron stays. Electron stays in the metal. And that's just it. That energy gets absorbed by the metal, and the electron just goes, yeah, okay, fine. I'm not bothered because I need 12 to escape. And the second one is we'll up our energy for the incoming light, and we'll say it's 12 units. So I've got my electrons in my zinc, and I've got my work function is 12 units as well. And the electron says, well, I need 12 units of energy. I need 12 to escape, but you're only giving me 12. So I get to leave. The electron says, I get to leave, but I do nothing else but just hang about over here. Okay, and nothing else happens. So you just get emitted, and that's it. The electron just gets there and stays there and doesn't really do anything. Okay, let's have our incoming energy is 14 units. And once again, well, you're getting all this drawn down very quickly. And the work function is still 12 units. Remember, the work function is a function of the metal. It's how much energy you need to supply to an electron to get the electron to leave. So the electron says, oh, right, okay, I need 12 to escape. And then I've got 2 left over. What do I do with the 2 units left over? The 2 units left over, after you've got the 12 just to escape to the edge, the 2 units left over are converted to kinetic energy. So it's 12 to get out, 12 units to just escape. The extra 2 are converted to EK, to kinetic energy, and that allows the electron to escape and to leave with some speed. And by using EK is a half mv squared, and we know the mass of an electron. We've done all this before when we did electric fields. We can work out the speed at which the electron zips off. Okay, so that gives you an idea and puts into perspective the sort of thing that we're talking about. All right. Now, what we need to do is actually work through all of that and get back to real life numbers that fit in with our actual amounts of energy, which aren't simple units like 10, 12, and 14. So we're going to do a complete worked example and go all the way through the worked example. We're going to use the idea of Einstein's formula equals hf. We're going to use the idea of the work function formula, and we're going to work out finally the speed of the electron. We're going to do the whole thing using some numbers, which you would be expected to do in any question. Right, okay. So, we're going to be given the amount of, we're going to be given the frequency of the incoming light. An incident is just like when you're doing reflection and refraction at National 5. It just means incoming. Incident means it's a photon that's coming in to the metal. The frequency of an incident photon is 1.5 times 10 to the power of 15 hertz. And the first part of the question is, we've got to calculate. The SQA paper would actually say calculate. They don't use words like what amount. They use special words, command words. So that really should be calculate, not what amount or how much energy. So I ought to take that out really and say calculate Okay, so it's an incoming photon. We know the formula, E equals HF, which is 6.63 times 10 to the negative 34 multiplied by our frequency, 1.5 times 10 to the power of 15 hertz. And we multiply those two together, and I think we get 9.45. You're going to have to check that. 9.45. Might be rounded up actually to 9.5. I'll just do that very quickly. 6.63 times 10 to the negative 34 times 1.5 times 10 to the power of 15 equals 9.945. I got that wrong. Thought I did. 9.945 times 10 to the negative 19 joules. Okay, do not round this up. Keep the figures because we're going to carry this on into the next part. Next part says, right, let's let me tell you what the work function is of the metal. And all we'll do is we'll use the E equals HF naught that we did earlier. I've rubbed it out now, but you'll have this in your notes a little bit earlier from copying down what I've got. And you were given a threshold frequency earlier on, and we worked out the work function, which we could say is W. That doesn't really matter, it's an energy, just W for work function. So I'm going to tell you that the work function is 6.760 times 10 to the negative 19 joules. And we did that earlier, so I could tell you the threshold frequency, and which is F naught. I could tell you the threshold frequency, and then you can multiply by Planck's constant, and you get the work function of the metal. But we did that earlier on, so not going to do that again. It's just using the same information we did earlier. And it's 6.760 times 10 to the negative 19. Now you can see when you look at this that this is the energy of the incoming photon, 9.945. It's got the same 10 to the negative 19. This is 6.760 times 10 to the negative 19. 9.945 is bigger than 6.760. So because the incoming energy is bigger than the work function, then the electron is going to get ejected. It's not less than, in which case it would have no effect. If that number was less than 6.76, the electron would do nothing. If it was exactly equal to 6.76, the electron would just be ejected and would stay there. But this is much bigger than that, so we're going to get the extra energy is going to get converted into kinetic energy. So the effect is that we've got the incoming or incident photon energy. It's entirely appropriate to mix your words. You can use incident, you can use incoming, it doesn't really matter. The incoming photon energy is bigger than, you'll be aware of that bigger than symbol from maths, is bigger than the work function. So we're going to look at option 3. So the extra energy is converted to EK. And what do I mean by the extra energy? Well, it's just the difference between 6.76 and 9.945 times 10 to the negative 19. So we can work that out. So the next bit is that was what is the effect. We can state what the effect is. That's another SQA command word, state what's going to happen. And you can just look at the numbers and you can make a statement. So the third part 3, and we can use the word ejected, we could use the word emitted, we could use the word escape. It doesn't really matter. What is the speed of the ejected electron? So we've got a formula, the excess energy which is the kinetic energy, that's equal to HF take away HF naught. In other words, it's the energy of the photon coming in and you take away from it the work function. and I think there's a version of this. I'm not sure if there's a version of this on the relationship sheet, but we just know it's the extra energy. So what was the energy of the photon coming in? It was 9.945 times 10 to the negative 19. And what's the work function? It's 6.760 times 10 to the negative 19 joules. You take one from the other, that tells you how much energy you've got left over, which is 3.185 times 10 to the negative 19 joules. So that's your excess energy that is converted to kinetic energy, and that will enable the electron to escape. So how do we work out what the speed of the electron is? Well, as we mentioned before, Ek is equal to a half mv squared. So I've got this number, and again, I haven't made this number shorter, 3.185. And the reason why I haven't made it shorter is I'm still using it in my calculations. If you shorten the number right in part 1, that gives you an error in part 2, which gives you an even bigger error in part 3. So it's only the very final answer that we need to have a look at, to 3 significant figures or 2 decimal places. So half I'm going to change to 0.5. Now m, you can look up the mass of the electron on the data sheet, 9.11 times 10 to the negative 31 kilograms. You'll be familiar with that number from before, and then we're going to multiply that by v squared. We're going to rewrite the formula. Again, you don't need to rewrite everything if you don't want to, but I'm just going to do the cross multiplying. 3.185 times 10 to the negative 19 divided by all of that, 0.5 times 9.11 times 10 to the negative 31. And that can go straight into your calculator. Don't forget, when you're dividing, you probably want to add the brackets. So you're dividing by the whole of that. And I will get 6.9. This is v squared still, 6.992 times 10 to the power of 11. And so v is the square root of that, which is 8.36 times 10 to the power of 5 meters per second. And that is a typical answer from a typical question, and it gives you a number round about 10 to the power of 5. Many of these speeding electrons leave at that sort of speed, something times 10 to the power of 5. Just a little bit bigger would enable you to have something times 10 to the power of 6. So these are the sort of size answers you're looking for. 3 significant figures or 2 decimal places. If you did all of this and you got a number with something like 8.36 times 10 to the power of 8, you instantly would say to yourself, no, that must be wrong. That must be wrong, because nothing can go faster than the speed of light. Remember, speed of light is 3 times 10 to the power of 8. That's the speed limit set by the universe, described by Einstein. So if I had 8.36 times 10 to the power of 8, I'd say, no, that can't be right. And you then have to go back and check up on your answers. Okay, I think this may be worthwhile putting it into some sort of box, and then we can just explain what everything is, just to do this fully. You've nearly got to the end now, and after this you'll be doing some problems yourself, so not got much longer to go with these sums. And then finally I'm going to finish off this lesson with an open-ended question, which we've not seen much of. So that formula Ek equals HF minus HF naught is on the relationship sheet, and this, we'll just write down what this is the kinetic energy. If you don't want to copy this down because you've understood it, that's okay. Kinetic energy of the ejected electron. This is the energy carried by the incident photon. And this is the work function of the metal. And that would provide a nice full SQA exam type question, which would work through the whole lot. And remember, this, if it's going to work, this has to be bigger than this. Because if it's less, it's not going anywhere. If it's exactly the same, you don't get any extra kinetic energy left over. Right, so that's the sums bit. I'm now going to do, just to finish, I'm now going to do an open-ended question, but I'm going to put the open-ended question, which looks at this stuff, into a separate little lesson, so that you can concentrate on doing that first, and then we'll come back and look at the open-ended question next. So I'm just going to stop this for now. Stop the recording, and you'll be able to view the open-ended question in a short additional video.